Alright everyone, welcome back to another video. So in this video we'll be covering time series. This will be our last topic of the module Advanced Modeling Technique. Now so far we have completed some really powerful methods in this module like discriminant analysis, clustering, principal component analysis, support vector machines, association analysis, and the mighty neural network. Now let's see what we are going to cover in time series. In time series, we'll first obviously see what is a time series. Then we'll see what are the different types of time series model, which are additive and multiplicative. Then we'll see the method to model time series, that is Box Jenkins Method. Then we have random walk method, then exponential smoothing. And then we'll do 2 assignments on time series to further reinforce our understanding. Now guys, before we start, I would like to state that time series is a huge topic. And in fact, you will even find books written on it. So it's really not possible for me to complete it in a short video. But consider this as a foundational knowledge for time series. And after this, you will have a pretty good idea about the nitty-gritties of time series. And as and when required, you can build upon that foundation and master it. So without further ado, let's begin with the topic and let's see what is the definition of time series. So time series is the arrangement of statistical data in chronological order. Or in other words, time series data means the data is in a series of a particular time period or intervals. For example, annual profits, quarterly sales revenue, rainfall data, monthly website traffic, etc. are few examples of time series. Now there could be a univariate time series, which means single variable, such as periodic temperature data, or there could be a multivariate time series, such as periodic temperature and humidity data. So the data that we had seen so far in model building was cross-sectional data, which is the data of one or more variables collected at the same point in time. Now we are going to work on the time series data. We just discussed that this is a set of observations or the values that a variable takes at different times. Then we also have a pooled data, which is a combination of time series data and cross-sectional data. Now the next question is, how does the time series looks like in R? Well, you can think of a time series as a list of numbers along with some information about what time those numbers were recorded. So this information can be stored as a time series object in R. Now if the data is not already a time series object, then we can convert the data into a time series object when working in R. We will see this how we can do it when we'll do the assignments. Alright, so this was the basic definition of time series. Now let's move on to the next topic, that is time series modeling. So in this section we'll see how can we model time series data. Now there are 2 types of modeling for a time series data. First is the additive modeling, which is given by the following equation. Here yt is a response variable as a function of time that is being modeled here. Now on the right hand side, the first 3 components are called the deterministic components and the last component is the random component. mt here is the trend, st here is the seasonal component and ct is the cyclic component and et here is the random or irregular component. Don't worry, we'll see the definition in a while. But before that, let's see what is the second type of model. The second type of model for time series is multiplicative modeling, which is given by the following equation. Now here everything remains the same except that it is being multiplied instead of addition. We can transform it into an additive model by taking log of it, and then it can be treated as an additive model. Now the next question is when to use which model. So the additive model is used when the seasonal variation is relatively constant over time, and the multiplicative model is useful when the seasonal variation increases over time. We will see what are the seasonal variations, but this is how we decide which model to be used when. Now let's discuss each of the components of the model which are shown here. So we already know what trend is. We use it in our daily life as well. But by definition, the trend shows the general tendency of the data to increase or decrease during a long period of time. So basically it refers to a change in the mean over time. After that we have seasonality. It is a variation that occurs at specific intervals. The intervals are less than a year, such as weekly, monthly or quarterly. Third, we have cyclic variations. So cyclic variations in a time series are those variations which operate themselves over a span of more than 1 year. So unlike seasonal variations which operates within a year, cyclic variations span over more than a year. Now the fourth and the last component is random/irregular movements. These are the fluctuations that are unforeseen, uncontrollable, unpredictable and are erratic. These forces could be earthquakes, wars, floods, famines and any other disasters. These are those variations which are not in our control. So these are the four components of a time series model. Now if we plot the time series data on a graph, then it will look something like this as shown here. Now to model time series there are different methods available, but one of the most common and popular ways of studying time series is Box Jenkins method. So let's see how do we model time series using Box Jenkins method. Basically there are two steps in Box Jenkins method. In the first step, we estimate and eliminate the deterministic components if they are present in the model. So we check for their presence and if they are present, then we remove it and move to the next step. In the second step, we model the residual using ARIMA models. ARIMA stands for Auto-Regressive Integrated Moving Average Models. So there are basically four steps in ARIMA modeling. First step is to check for stationarity. And then we make the time series stationary if it is not already. Now what is stationarity? We'll see it in a while. But for now, just get familiar with these steps. Then the next step is identify the order of the ARIMA model. And after that, we will fit the model. And finally, in the fourth step, we forecast or predict the future values. So that's it. These are the steps involved in Box Jenkins method. We'll see these steps in detail in the upcoming slides. Now, before moving forward, let's understand one more important concept, that is decomposition of time series. Decomposition helps us understand the time series better for forecasting. So it is basically splitting the time series into three components, that is trend, which includes the cyclic component, seasonality and residual. Now in other words, you could say that's what Box Jenkins method do in this step 1 that we saw earlier. Now let's proceed further to understand the Box Jenkins method in detail. So the first step we saw was to estimate and eliminate the deterministic component. And we already know that there are three deterministic components, that is trend, seasonality and cyclicity. So we will see how do we determine each of these. So let's start with trend. So in the first step, we'll check the hypothesis for presence of trend using relative order test. Because to estimate the trend, we should first know whether the trend is present or not. So the presence of trend can be checked using relative order test. Now in the next step, we will assign Qij a value equal to 1 or 0. So let's say y1, y2 up to yn is our time series. So we will check the previous value of y with the next value of y, and if it is greater than the next value, then it will be 1, else it will be 0. So that's how we will assign Qij a value of 1 or 0. Now let capital Q be the number of decreasing points or discordance given by the summation of small qij. Then we'll find the expected value of Q using this formula. After that, we'll find the Z statistic as shown here. And then as usual, we'll use Z statistic to test the hypothesis. And if H0 is rejected, then it means trend is present. And then we'll check if the capital Q is greater than its expected value. If yes, then it will be a falling trend. If it is lesser than the expected value, then it will be a rising trend. So that is how we carry out the relative ordering test to check the presence of trend. Now obviously these steps will not be performed manually. I have just shown these steps to explain the working. All these steps will be done by R using a single command. Okay, so now once we have ascertained that trend is present, then the next step is to estimate the trend. There are two methods to estimate it. The first is the least square method, which is given by the equation shown here. Here delta is nothing but the remaining components, which are seasonality, cyclicity and randomness. We estimate the trend by minimizing the delta. Then the next method is moving averages method. Here the trend is calculated using moving averages with an appropriate span. So moving averages is nothing but you simply average the readings over a span instead of taking it over the entire data at one time. So to calculate the moving averages, there are different formulas based on your span. If it is an odd span, then you use the first formula. And if it is an even span, then you use the second formula. Now obviously you don't have to remember all these formula. Just have a look at it and move on. Now the question is how to select the appropriate span. So we take the appropriate span of the moving averages as the arithmetic mean of the periods between different peaks in the observed time series. In case you still don't understand what moving averages is, just Google it. It's a pretty simple technique. So we have checked the presence of trend and the trend was present. Then we estimated what is the trend, and after estimating the trend, the third step is to eliminate the trend. So the simplest method for eliminating the trend is subtraction. In this method, trend eliminated series can be obtained as YT minus MT, where MT is the estimated trend. There are other methods as well, such as quadratic, moving averages, etc. The selection of method is specific to your field. However, in general, we use subtraction as it is the simplest method. After estimating and eliminating the trend, we will go for the second deterministic component, that is seasonality. So again, before estimating the seasonality, we will check for the presence of seasonality using a hypothesis test. So we will use Friedman test to detect this seasonality. Now I am skipping the details as all these things will be done by R. However, if you are curious about it, then you can Google it and you can get to know more about it. Now once seasonality is detected, then we'll proceed to estimation and elimination step. So for estimation of seasonality, we again have two methods. First method is small trend method. We use this method when trend is small, that is, the trend is constant within a year. So we first estimate the trend as average within the period of seasonality. The period of seasonality could be 3, 4, 12, etc. Then we will use the formula for seasonal component to calculate it. The second method for estimating the seasonality is rapidly changing trend method. Sometimes what happens is the trend is volatile and changes within a year. In that case, we use this method. So first we estimate the trend using moving averages method within the period of seasonality, and then after calculating the trend, we detrend the data. And then we can use the detrended data and put it in the formula shown here to calculate seasonality. So that is how you get seasonality using this method. Now the last step is to eliminate the seasonality. We can again use subtraction method to calculate the series without seasonality as shown here. Now the cyclicity component is generally taken as absent in series not involving too many years. So for now we'll also not be going into the details and we'll be skipping this. Now the final step is to make the forecast of the deterministic components. So the ultimate goal is to forecast values of the observed series for future time points. That is model trend, seasonality, cyclicity is generally ignored, and random error and forecast it. Now there are many methods for forecasting, such as knife forecast, moving averages forecast, ARIMA, growth forecast, linear regression, exponential smoothing, etc. So in this video, we will be seeing naive forecast, ARIMA, linear regression, and exponential smoothing. As far as linear regression is concerned, we already have the basic understanding of linear regression. So we will not go into the theory part, and we will directly implement it in R during the assignment part. So let us see our first method, that is naive forecasting. Now naive forecasting is also known as random walk. This model assumes that in each period, the variable takes a random step away from its previous value, and these steps are independently and identically distributed in size. The formula for random walk is shown here. Now the forecasts from a random walk model are equal to the last observation, as future movements are unpredictable and are equally likely to be up or down. So the random walk model may look trivial if you have never seen it before, because what could be more simple-minded than always predicting that tomorrow will be same as today? So this does not even require any knowledge of statistics, because all of us do this in our daily lives as well. But believe me, this method works remarkably well for many economic and financial time series data. And for this reason, it is sometimes called as naive model or persistent model. Now we have one variant of this method as well, which is called random walk with drift. In this case, the forecasts are allowed to increase or decrease over time. Now this amount of change over time is called the drift, which is shown here by alpha. So here alpha is considered to be the average change seen in the historical data. So this was all about the naive forecast method. Now our next method is exponential smoothing. Forecasts produced using exponential smoothing method are nothing but weighted averages of the past observations. And these weights keep on decaying exponentially as the observations get older. Now one common method for doing exponential smoothing is Holtz-Winter smoothing method. Now I am not going into the details of it. You can Google it and find out more about it if you wish to understand the maths behind it. But we can skip the maths as it is not that important to know the maths behind it. We can let R do the calculations. But still, if you think you need to know it, you can Google it. Now it has three smoothing parameters, alpha, beta and gamma. And they are found out by minimizing RMSE. We will see its implementation when we will do the assignment in R. So that is how we use exponential smoothing. Now another technique is ARIMA model, which is a form of Box Jenkins method. Recall our second step of the Box Jenkins method. The second step was to model residual using autoregressive integrated moving average method. Also recall the additive decomposition of the time series that we had studied in the beginning. So during the first step, we have estimated the deterministic component, that is MT, trend, ST, seasonality, and CT, which is cyclicity if it was present. And then after estimation of the deterministic component, we remove the deterministic component using the subtraction method. And then we obtained this residual series. Now this residual series will be modeled using ARIMA modeling. So let's understand what ARIMA models are. So as we already know, ARIMA stands for autoregressive integrated moving averages. And it is written as ARIMA within brackets PDQ. Now these PDQ determine the order of ARIMA. We'll see how to calculate PDQ in a while. Mathematically, we can write the ARIMA model by using this big equation as shown here. Well, this part of the equation is called as autoregressive model, and this part of the equation is called as moving averages model. And epsilon t is the residual series. Now if you refer to the AR model given in the above equation, you can see that epsilon t depends on its own lags. That is epsilon t minus 1, epsilon t minus 2, up to epsilon t minus p. That means up to p lags. Now this p is the order of the AR model, that is autoregressive model. While on the other hand, if you look at the right hand side of the equation, which is the MM model, here epsilon t depends on a term called delta. You can think of delta in the above equation as the weighted moving average of the past forecast errors up to lag Q, and Q is the order of MA model, which is moving averages model. Now rest of the terms of the equations are given here. You can read it here. You can see here phi is the AR model's coefficient and theta is the MA model's coefficient. Also, if you see the last term here, which is D, this is the degree of differencing to make the series stationary. Now we will see what stationary series are. So we will also learn what differencing is. So finally, the order of ARIMA is defined by P, Q and D. P and Q are the lags of AR and MA model respectively, and D is the degree of differencing which is required to make the series stationary. So now let's see what a stationary series is. A time series whose properties do not depend on the time at which the series is observed. Basically, the mean and variance is constant over time for this series. Any time series with trends or with seasonality are not stationary series. In general, a stationary time series will have no predictable pattern in the long term. Now obviously we will not look at the graph to check the stationarity. So we use Dickey-Fuller test to check if the series is stationary or not. Here the null hypothesis is that the process is not stationary, and alternate hypothesis is that the process is stationary. Now again, no need to go into the details of this test. It can be easily done in R. So we'll skip the details. Now the next question is, what if the series is not stationary? So to make the series stationary, we do differencing. Now in differencing, we keep on differencing the series until it becomes stationary. So sometimes the first order differencing makes the series stationary. Sometimes we have to do the second order differencing to make the series stationary, and so on. Now this order of differencing is used to determine the order of ARIMA, which is given by D. So when we difference the value from its previous value, then it is called first order differencing. But sometimes first order differencing does not work. So we go for second order differencing as shown here. And it is very rare that we go beyond second order differencing. But I hope you have got the idea how differencing works. So let's move on to the next part. So there were three terms that are required to determine the order of ARIMA. It was P, D and Q. So we have already seen how to determine D. Now the remaining two terms that are required to determine the order of ARIMA are P and Q. So let's see how do we determine P and Q. So we use correlogram or ACF, that is autocorrelation function plots. And we also use partial correlogram, which is PACF. And the third metric that we use is AIC. So let's first see what is autocorrelation function. So autocorrelation function of time series at lag h is defined as linear dependence between the original series and series with lag h. So basically when you have a series of numbers and there is a pattern such that value in the series can be predicted based on the preceding values in the series, then the series of numbers is said to exhibit autocorrelation. So that is what autocorrelation function is. So we use ACF and PACF to check this. Now what is an ACF plot? So it is the plot of autocorrelation functions for different lags, say 0, 1, 2 and so on, of the given time series. This is also called as correlogram. After that we have PACF plot, also known as partial correlogram. This is the plot of partial ACF for different lags like 1, 2 and so on of the given time series. So PACF gives the partial correlation of a stationary time series with its own lagged values. Now you may ask, what is partial correlation? So partial correlation is a measure of the strength and direction of a linear relationship between two continuous variables whilst controlling for the effect of one or more other continuous variables. So basically it measures the strength and direction of linear relationship while controlling any other effect by any other variables. So as you can see here, we can find correlation between y and x3 while controlling the effect of other two variables, which are x1 and x2. So this is what partial correlation is. Now here is a small table that shows us how do we determine the order of P and Q using ACF and PSCF. Just have a look at it and keep this table in mind. We'll see the plots in the assignment and we'll see how do we decide the order using ACF and PSCF plots. Now the other method to determine the order of P and Q is using AIC. There are times when we don't get a clear-cut picture from the above plots. In those cases, we use AIC. The idea behind using AIC is simple. We build several models with some arbitrary values of P and Q. Generally, these values range from 0 to 7. And then we select the ARIMA model with the least value of AIC. So that is how we decide the order of P and Q using AIC. Now based upon the order of ARIMA, we get different models as shown here in the table. So the first model is white noise. In this case, P, D and Q values are 0. So a time series is said to have white noise when it shows no autocorrelation. Here ACF value is close to 0 and it lies between plus minus 2 divided by square root t. Here t is the length of the time series. Forecast errors become white noise here, hence all information in the model is harnessed by the time series. Then as given in the table, second type of ARIMA model is random walk. If we have P and Q equals to 0 and the order of differencing is 1, then it will be a random walk. Remember, in random walk, forecast values depend on the previous observation. Hence an ARIMA model with values of P and Q is equal to 0 and D is equal to 1 is called as random walk. Then the third model given in the table is random walk with drift. This also has P and Q is equal to 0 and D is equal to 1. And then we have AR model if Q and D is equal to 0 and MA model if P and D is equal to 0. Now that is all from time series, guys. It was indeed a long one and had a lot of details. But as I said earlier, this is a very vast topic in itself and there are complete books that are written on this topic alone. So consider this as a tip of an iceberg only. I tried my best to cover the necessary details and in the simplest way. I hope you were able to understand it. If not, then do watch the video again, or you can even Google more about it and get to know more about this topic. So if you Google it, you will come across with a lot of details given on internet. But now at least you know what are the important topics to cover first and what are your doubts. Anyway, let's quickly see what we did in this section. So first we understood what is the concept of time series. We saw the two modeling approaches of time series, the additive and multiplicative modeling. Then we learned the most commonly used method, that is Box Jenkins method. Here we learned about the decomposition of time series and ARIMA modeling. We also touched upon random walk, the simplest approach for time series, and exponential smoothing as well. Okay, so now it's time to do assignments. So there will be 2 assignments on this topic. Alright, so I'll catch you up in the next video where we'll do our first assignment.